This video will demonstrate how to do both types of chi-square analysis in R. So first we just need to run our setup chunk, and then we're going to read in our data as usual. This time we are using the Adelaide survey. So this was survey data from people in Adelaide, Australia. And so we have several variables: sex, their writing hand, their pulse, how much they exercise, how much they smoke, and their age. And then first we're going to do a goodness of fit where we have equal expected values. And the way that the chi-square analysis works is a little bit different from most of the other analyses we have done, in that you don't just tell it the name of the variable, you actually have to give it the counts for each group within whatever category you are interested in. So in order to do that, first you have to figure out what those group sizes are, so we can run the table command for any variable in the data set to get an output of the frequencies for each group. And so here we see we have frequent, none, and some are our categories. So then we can create an object. You can call it whatever you want. I'm just calling it counts to be simple. And into that we put these values. So these values here match these values down here. Once you've created that object, then you can put that into the command for your chi-square test. Correct equals false tells R to not use the Yates correction because we just don't need it. So if we run this line, we create these counts. You can check on those. If you highlight just counts and run that, it'll give you back that information, right? That should match when you used the table function to get frequencies. And then you can run the chi-square test. And this is just the default output. So we have our chi-squared value, the degrees of freedom, and the p-value. Then the next thing we're going to do is add sort of two levels of complexity. The first thing we're going to do is to tell R that we have unequal expected values. And then we're also going to use a Monte Carlo simulation to get our probability value. That's one way to do randomization. So if we want just the default output, we can use the same structure as we did above. It's the same command, chi-square.test, counts. We're using that same data as we had before. We still want to not use the Yates correction. This part of the script tells R what probabilities we want to have for our expected values. So we're expecting the first two groups to have essentially 25% of the data within those, and then the last group to have half of the data. If we run this just counts again, we can look at the order of things. So we're saying that both frequent and none are going to be at the 25%, and people who exercise some are going to be 50%. And then this last piece, simulate.p.value equals true. That tells R to run a Monte Carlo simulation, and then this capital B equals 2000. That's how many random samples are going to be pulled in order to create that p-value. And so we'll run this one and just get our default output. So again, we get a chi-squared value. The degrees of freedom is NA, and that's always going to happen when you use the Monte Carlo simulation because degrees of freedom just doesn't apply in that case. And then you get your p-value again. All right, so this is a very small p-value, so there's a very small chance that the observed values match the expected values. And so in this case, we're saying we're actually not fitting our specific prediction of how our data are going to be spread out across those three groups. And then there's other output that you can get as well that can be useful, but in order to get that, you have to run your chi-square test, but put it into an object. And you can use any name that you want here. I'm just using good fit because this is a goodness of fit test. So you have to create that object first, and then you can ask for specific information from that object. And so we can ask for just statistic, and that will give us just the chi-square statistic. Degrees of freedom, remember that's NA because we use the simulation for our p-value. You get our p-value, And then we can also have it output our observed values, make sure that that's what we wanted it to be. Our expected values, in this case, this is based on 25%, 25%, and 50% of the total sample size. And then the residuals, I think this one is the most useful for being able to tell which of your groups is driving a difference if you are seeing one. And this is based on this equation here, so your observed minus the expected values divided by the square root of the expected values. That's very similar to what we used in class, which is why we can end up with some negative values. So we can see the people in the frequent group, right, that's where we see the biggest difference. We see the next biggest in none, and some was pretty close. So that can be especially useful for describing differences when you get a statistically significant chi-square test. Okay. And then the other test is this test of association. So this is where we're looking at two variables to see if they are related. And so first we have to figure out what the frequencies are within each of the cells. This time we're going to look at writing hand, so whether people are left or right-handed, and then sex. So if we run this first command, we see down here we have 7 females who are left-handed, 110 that are right, and then for males we have 10 left-handed and 108 right-handed. And so we want to know, is there, different proportions of handedness for females versus males. And so now when we create our counts, it's a little bit more complicated because we have to create a matrix. So we have to create something that looks like this. And so the way that I'm doing it here is this is the top row, 7 and 10, the bottom row, 110 and 108, and then we're telling it the data are being entered by row. So that's why this says true. If you entered the data by column, then you would use false here. So if you entered 7, 110, 10, 108, and you use by row equals false, it would still set things up the way you wanted it to. And then you tell it the number of rows. And so it's 2 rows, and since you give it 4 data points, it knows to put 2 of those in each of the rows. So we can run that and then look at the counts object and make sure this looks the way we want. So notice we lost our labels, but if we forget, we could always rerun this table command to get the labels put back in there. Okay, so just the default output is the same test as above. And so R can just figure out, based on the structure of the data, whether you're doing a goodness of fit test or if you're doing a test of association. So since we have a matrix now with multiple rows, R knows that this is a test of association. And so you get similar output to above, a chi-squared value, a degrees of freedom, and the p-value. We can also do Fisher's exact test. And so this gives us also a p-value. It tells us what our alternative hypothesis is. It gives us a 95% confidence interval around the odds ratio. And then if we want to do that Monte Carlo simulation, the same command as above, the simulate.p.value equals true. And here we're doing just 1,000 random samples. So similar outcome here with our chi-squared value, degrees of freedom that don't mean anything, and our p-value. And you can see here that this p-value is quite large. So it looks like handedness and gender are not related, at least within this data set. And then we can get more specific output, again, by taking our chi-square test function, but then putting it into an object. This time I just called it test assoc for test of association. And then we can use the same commands as above to get our chi-square statistic, the degrees of freedom, the p-value, the observed values, that's just the information we gave it, the expected values, so this could be interesting. This is those expected values for each square, and then our residuals to see. We've got bigger differences on our top row than we do on our bottom row, but still it's not enough to have statistically significant chi-square value. And that is all.